Okay, second law of thermodynamics. The thermodynamic state quantity that measures the randomness or disorderliness of the molecule in a system is called entropy. Other definitions, Kelvin-Planck's statement, it is impossible to construct an engine which operating in a complete cycle will absorb heat from the single body and convert it completely to work without leaving change in the working system. Clause's statement, it is impossible for self-acting machine unaided by the external agency to convey heat from a body of lower temperature to another higher temperature. That is, it cannot pass itself from colder to hot body. It is impossible to construct a machine operating in a cycle that will convert heat into work without producing any other changes in the surroundings. Entropy is denoted by the symbol S. More is the randomness of the system, more is the entropy. For example, if we hit any object, the velocity of molecules increases and hence the disorderliness also increases. It means that entropy of the substance is increases. If the system absorbs Q amount of heat at temperature T and the increase in entropy of a system is given by delta S equal to Q over T. If system absorbs Q amount of heat, Q will be positive, entropy change will also be positive. Positive delta S indicates that entropy of system increases. So delta S system equal to dq reversible over T. Heat absorbed by the system is taken as positive. If the system lost Q amount of heat, Q will be negative. Negative delta S indicates that entropy of system decreases. So delta S surrounding equal to minus dq over reversible over T. Heat lost by the surrounding is taken as negative. So delta S universe equal to delta S surrounding plus delta S system equal to dq reversible over T plus minus dq reversible over T equal to 0. All spontaneous processes are accompanied by increase in entropy. Work done by the system W irreversible is less than W reversible. So W irreversible less than W reversible. But entropy of the system is same as it is state function. That is, the increase in entropy of the system is same as irrespective to the process carried out reversibly or irreversibly. So delta S system equal to Q reversible over T equal to constant. But Q irreversible is greater than Q reversible. It lost by surrounding. Q irreversible is then Q reversible. However, heat lost by surroundings can be taken as infinitesimally slowly, that is reversibly entropy change of the surroundings. Total entropy change of universe equal to delta S total equal to delta S surrounding plus delta S system. So dq reversible over T plus minus dq irreversible over T. So dq irreversible greater than q irreversible. So dq reversible over T minus dq irreversible over T greater than 0. Hence, delta S universe equal to delta S surrounding plus delta S system greater than 0. Thus, entropy of universe always tends to increase in irreversible process at constant temperature. Cyclic process, when a system in a given state goes through a number of different states and finally return to the initial stage to complete a cycle, such type of process is called cyclic process. For cyclic process equal to constant d equal to 0, Carnot cycle is a hypothetical, ideal, and reversible cyclic process proposed by French engineer Sadi Carnot to demonstrate the maximum convertibility of heat into works. An ideal machine to demonstrate this cycle is called Carnot heat engine. A Carnot cycle consists of 4 different operations, which is represented in a pressure volume diagram as shown below. For schematic diagram of Carnot cycle, isothermal reversible expansion, A to B, B to C, C to D, D to A, isothermal reversible expansion, adiabatic reversible expansion, isothermal reversible compression, adiabatic reversible compression. 。 . 。 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 。 。 . 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 。 . 。 。 . 。 . Isothermal reversible expansion when a cylinder is placed in a heat reservoir at higher temperature T2 and expand isothermally and reversibly from V1 to V2 for operation change in internal energy delta E equal to 0, so heat absorbed by the substance. Q2 equal to work done W1, but from the isothermal reversible expansion work done W1 equal to Q2 equal to RT2 ln V2 over V1. Adiabatic reversible expansion, now the gas is allowed to expand adiabatically, reversible from V2 to V3. Then the temperature of the system falls from T2 to T1. From this operation Q equal to 0, so work done W2 equal to minus delta E. From the definition of molar heat capacity at constant volume, Cv equal to delta E over delta T, work done W2 equal to minus delta E. So minus delta E equal to minus Cv delta T equal to minus Cv T1 minus T2 minus Cv delta T, Cv T2 minus T1. Substituting the value of delta E in the above expression, W2 equals Cv T2 minus T1. Isothermal reversible compression. On doing this compression at constant temperature T1, the volume of decreases from V3 to V4. For this process, delta equals 0. Work done by the system during this compression minus Q1 equal to W3 equal to RT1 ln V4 over V3. Adiabatic compression. On doing this compression adiabatically from changes from V4 to V1 and temperature becomes T2, so work done by the system doing this compression minus W4 equal to minus Cv T2 minus T1. The net heat absorbed by the system Q equal to Q2 minus Q1. So in solving, we get W equal to RT2 ln B2 over B1 plus RT1 ln B4 over B3. From the equation 6 and 5, W equal to Q. So we get for the adiabatic process, Tb gamma minus 1 equal to constant for called Bc, T2 B2 gamma minus 1 equal to T1 B3 gamma minus 1. So T2 over T1 equal to B3 gamma minus 1, B2 gamma minus 1. For core D, T2 over T1 equal to B4 gamma minus 1, B1 gamma minus 1. From equation 8 and 9, we get V1 over V2 equal to V4 over V3. Now equation 6 becomes W equal to RT2 ln V2 over V1 plus RT1 ln V1 over V2 and W equal to R ln B2 over B1 T2 minus T1. So RT2 ln B2 over B1 plus RT1 ln B1 over B2. We get Q2 minus Q1 equal to R ln B2 over B1 T2 minus T1. In the Carnot cycle, heat converted to work is W equal to Q2 minus Q1. Efficiency of work done in Carnot cycle, neta equal to heat converted into work over heat taken from the source. So we get thermodynamic efficiency of Carnot cycle. Thermodynamic efficiency is the ratio of the work obtained in a cyclic process to the amount of heat absorbed from the source, which is denoted by symbol neta, and neta equal to W over Q2. So equation 1 becomes neta equal to T2 minus T1 over T2. From the Carnot cycle, we have the Q2 equal to RT2 ln B2 over B1, W equal to R ln B2 over B1, T2 minus T1. Substituting the value of W and Q2 in equation 1, we get neta equal to T2 minus T1 over T2. From the equation 3, we get conclude that the neta depends upon the temperature difference between T2 minus T1. Higher is the difference in the temperature between source and the sink, greater will the efficiency. If T1 equal to 0, neta equal to 1, this implies that W equal to Q2, that is entire heat is converted into absolute 0. Higher temperature complete conversion of heat into work may be possible, but absolute Carnot is realized in actual practice. Therefore, no heat engine can be constructed whose efficiency is 100%. When T1 equal to T2, the value of neta is 0. That is, the no work can be produced when the engine operates under the isothermal condition. Mathematical formula entropy from Carnot cycle, we know that thermodynamics efficiency Carnot cycle, neta equal to Q2 over Q1 over Q2, T2 minus T1 over T2. Equation 1 is derived giving the positive sign to the heat absorbed Q2 and negative sign to heat loss Q1 system. So equation 1 may be. Let us consider our system going in reversible manner from the initial state A to B through parts and back to A through the part second. This cyclic process consists of number of Carnot cycles, which is represented as below. Figure a reversible process, number of Carnot cycles. When the isothermal and adiabatic process in a Carnot cycle are carried out reversibly, the summation of Q over T terms is equal to 0. So summation Q over T equal to 0. Infinitesimally small change summation dq over T equal to 0. Since the cycle is profound in the two steps from A to B and B to A, the summation dq over T equal to integrating A to B dq over T plus integrating B to A dq over T equal to 0. The integral A to B dq over T is the summation of all the dq over T terms when the system changes from A to B along the path first, and B to A dq over T is the similar integral terms when the system returns from B to A along the path second. Thus, A to B dq over T part first and minus B to A dq over T part second, A to B dq over T part first, A to B dq over T part second. It is evident that A to B dq over T is a definite quantity and is independent with the part, and it depends only initial and final state of the system. This state function is entropy and denoted by S. So delta S equal to SB minus AC, A to B dq over T, delta S equal to dq over T for infinite change, ds equal to dq over T for infinitesimal small change. Physical significance of entropy, it is the measure of the disorderliness of the system. Entropy is the measure of the randomness or disorderliness of system, ice, water, vapor. There is increase in entropy and increase in the randomness of atoms, that is disorderliness of atoms. All natural and irreversible processes are accompanied by increase in entropy. Entropy and thermodynamics probability, qualitative entropy more than disordered, more likely states will dominate time, that is the higher entropy. So more the entropy, more is the thermodynamic probability. So S equal to KLNW. Entropy change in unavailable heat energy. In a reversible Carnot cycle, it is observed that only a portion of heat energy absorbed by the system is converted into work, and the remaining portion of the heat is rejected. The heat absorbed by the system from the source is called available heat from the efficiency Carnot cycle. So we know that neta equal to Q2 minus Q1 over Q2 equal to T2 minus T1 over T2, and we get, so Q1 equal to delta S system into T1, where delta S system is Q2 over T2 From equation 2, it is evident that the heat energy which is not converted to work is equal to the product of entropy change and temperature. In other words, heat unavailable for doing work is used to increase the entropy and temperature sink. Entropy change of system, surrounding, and universe. Energy change in universe. The universe is composed of the system and the surrounding, so that delta S universe equal delta S system plus delta S surrounding, delta S universe greater than 0. Entropy change in system and surrounding. Heat that flows into or out of the system also change the entropy of the surroundings. For isothermal process, delta S surrounding equal to minus Q system over T. Constant pressure Q system equal to change in enthalpy equal to delta S, so that delta S surrounding equal to minus delta S over T. The entropy change in the surrounding is equal to the amount of heat gain or loss. So Q surrounding equal to minus Q system. The Q surrounding, delta S surrounding is also inversely proportional to temperature. So delta S surrounding equal to minus delta S system over T. Entropy change in isothermal and adiabatic process when the expansion of a gas carried out under isothermal and reversible condition. The internal energy change delta E equal to 0 and first law of thermodynamics becomes Q reversible equal to W. The work done in the expansion of n mole of gas from volume V1 to V2 at temperature T is given by the equation. W equal to 2.303 nRT log V2 over V1. Comparing equation 1 and 2, Q equal to 2.303 nRT log V2 over V1. From the definition of entropy, we have delta S equal to Q over T, substituting the value of Q in equation 3, and we get delta S equal to 2.303 and our log V2 over V1. Relation between the enthalpy at change and entropy change. We know that enthalpy is equal to E plus PV. Differentiating the equation, we get ds equal to d plus pdv by dv. From the first law of thermodynamics, we have dq equal to d plus pdv. From second law of thermodynamics, we have ds equal to dq over t, dq over t equal to tds. From equation 3 and 4, tds equal to d plus pdv. From equation 2 and 5, ds equal to tds plus bdp. Entropy change during the expansion of ideal gas. When T and V are two variables, let us consider the case of the ideal gas where the temperature and volume are two variables. The increase in entropy of a gas for infinitesimally small change ds equal to dq over T. From the first law of thermodynamics, dq equal to d plus pdv. From the definition of molar heat capacity at constant volume, Cv equal to d over dt. D equal to Cv dt, substituting the value of d in equation 2, dq equal to Cv dt plus pdv. For n mole of ideal gas, above expression can be modified as dq equal to n Cv dt plus nRT dv over b, substituting the value of dq in equation first, and we get ncv dt over t plus nr dv over b in equation 5. Integrating equation 5 between the two limits, then we get delta S equal to ncb ln t2 over t1 plus nr ln b2 over b1. Equation 6 is the required equation for entropy change when temperature and volumes are the variables. When T and P are two variables, if P1 is the initial pressure and P2 is the final pressure of the ideal gas, then ideal gas equation for initial and final state is P1 V1 equal to nRT1, P2 V2 nRT2. Dividing the equation 8 by the equation 7, we get B2 or B1 equal to P1, T2 equal to P2 T1. From the relation Cp and Cv, Cv equal to Cp minus R, Substituting the Cv and B2 over B1 in equation 6, delta is equal to n Cp minus R, ln T2 over T1 plus nr ln P1 T2 P2 T1. 2.303 n Cp minus R log T2 over T1 plus 2.303 nr log P1 T2 P2 T1. Delta S equal to 2.303 NCP log T2 over T1 plus 2.303 NR log P1 over P2. Equation 11 is the required equation for entropy change when temperature and pressure are two variables. For isothermal process T1 equal to T2, so entropy change delta S equal to 2.303 NCP log T2 over T1 plus 2.303 NR log P1 over P2. So delta S equal to 2.303 NR log P1 over P2. For isochoric process, if P1 equal to P2, so entropy change delta is equal to 2.303 NCP log T2 over T1 plus 2.303 NR log P1 over P2. So delta is equal to 2.303 NCP log T2 over T1. Gives free energy, it is the quantity that is used to measure the maximum amount of work done in the thermodynamic system when temperature and pressure are kept constant. Mathematically, G equal to S minus Ts, G equal to E plus PV minus Ts. So differentiating equation 1, we get equation 2. Also, we know that ds equal to dq over t. So d plus pd over t and tds equal to d plus pd. So from equation 2 and 3, we get dg equal to bdb minus ht equation 4. At constant pressure, dp equal to 0, 0 dg equal to minus sdt. In terms of partial change, dava g over dava tp equal to minus s. Equation 5 represents the variation of Gibbs free energy with change in temperature and decrease in the entropy. Okay, second, at constant temperature, dt equal to 0. From equation 4, dg equal to bdp minus sdt. Bdp, equation 6. In terms of partial change, equation 6 can be written as dava g over dava p, t equal to b, equation 7. Hence, the change in Gibbs free energy with change in the pressure at constant is the measure of the volume of the system. Equation 6 can be written as because B equal to nRT over P, so dg equal to nRT over P dP. When pressure is changed from P1 to P2, the Gibbs free energy also changes from G1 to G2. The change in can be obtained integrating equation 8. So G2 minus G1 equal to nRT P2 over P1, delta G nRT ln P2 over P1, delta G equal to 2.303 nRT log P2 over P1. Question 9 and 10 show the variation of Gibbs free energy with change in the pressure or constant temperature for n mole of ideal gas. Work function, it is also known as Helmholtz free energy. Thermodynamics Helmholtz free energy refers to the thermodynamics potential facilities. The measurement of the useful work is obtainable from a closed thermodynamic system at constant volume and temperature and denoted by A. Mathematically, A equal to E minus Ts, where E equal to internal energy as entropy. Differentiating equation 1, we get d equal to dA minus tds minus sdt. Equation 2, according to first law of thermodynamics, dq equal to d plus pdv. From second law of thermodynamics, ds equal to dq over t, so tds equal to dq. From equation 3 and 4, tds equal to d plus pdv, d minus tds equal to minus pdv. From equation 2 and 5, d equal to minus pdv minus sdt. Equation 6 can be studied either at constant volume or constant temperature. Case first, at constant volume, dV equal to 0, dA equal to minus sdt. In terms of partial change, equation 7 can be expressed as dava A over dava TV equal to minus S. From equation 8, it is concluded that variation of work function with temperature is the measure of decrease in entropy. Case second, at constant temperature dt equal to 0, equation 6 can be written as d equal to minus pdv. Equation 9. In terms of partial change, equation 9 can be expressed as dava A dava vt equal to minus p. Equation 10. Equation 10 shows that variation of work function with volume of constant temperature is the pressure of decrease on the pressure. Equation 9 also can be written as P equal to nRT over B, so dA equal to minus nRT over B dV. When volume is changed from V1 to V2 at constant temperature, then work function also changes A1 to A2. The change can be obtained by integrating equation 11. So integrating a1 to a2 dA equal to nRT, b1 to b2 dV over b. So a2 minus a1 equal to nRT minus nRT ln dV over b. So delta A equal to 2 minus 2.30 nRT log V2 by V1. Equation 11 and 12 shows the variation of work function with volume at constant temperature for n mole of ideal gas. Criteria of spontaneity and equilibrium in terms of entropy and free energy when a process takes place with its own accord without the aid of external agency to achieve the thermodynamics equilibrium condition, then it is called spontaneous process. Spontaneous process is irreversible process, that is the natural process. Also, thermodynamic spontaneity and equilibrium condition can be interpreted in terms of change, entropy, work function, gives free energy. Criteria in terms of entropy change. Entropy is the state function. The change in the entropy should be same reversibly or irreversibly, but small change in the entropy is reversible process. The D is equal to D Q reversible over T. So TdS equal to D Q reversible. We know that dQ equal to D plus PdV, first law of thermodynamics. TdS equal to D plus PdV implies for reversible process if the same change for the same system is brought about irreversibly, then the entropy change remains same because it is state function. For irreversible process, the heat change is lesser than that for the reversible process, that is the Q reversible greater than Q irreversible. TdS greater than D plus PdV implies irreversible process. Combine equation 2 and 4. TdS less than greater D plus PdV. Equation 4 can be written as ds less than greater D plus PdV over T. Equation 6. If E and B are constant, then D equal to 0, dV equal to 0. So dava is E1, B1 less than greater than 0. Equation 7. So dava is EV less than greater than 0. The process is reversible. That is the process equilibrium. Dava is EV greater than 0. That is the value of dava is positive. The process is spontaneous. Criteria in terms of work function A from the equilibrium A equal to E minus Ts, dA equal to D minus TdS minus SDT. So dA plus SDT equal to D plus D minus TdS. From the equation 5, TdS less than greater D plus PdV. Minus PdV greater than D minus TdS. From the equation 9 and 10, minus PdV greater than dA plus SDT. So 0 greater than PdV plus dA plus SDT. If T and B are constant, PdV equals 0, SDT equals 0, then 0 dA over TV, equation 11. We can conclude from the equation 11 that by TV equals 0, the process is reversible, that is equilibrium. Criteria in terms of free energy from the definition G equal to S minus Ts, dG equal to ds minus SDT minus TdS, dG equal to d E plus PV minus SDT minus TdS, dG equal to d plus PdV plus VdP minus SDT minus TdS. Equation 12. From the equation 5, TdS less than greater d plus PdV. Equation 13. From equation 12 and 13, we get dG equal to VdP plus minus SDT, dG minus VdP SDT plus SDT less than greater 0. Equation 14. Keeping P and T constant, we get dG PT less than greater 0. Equation 15. Thus, for spontaneity, dG Tp equal to less than greater 0. For equilibrium and reversible process, dG Tp equal to 0. Equation 17. Okay, it's all about thermodynamics under B.Sc. second year, Institute of Science and Technology, Tribhuvan University. And please you all like, comment, share, and subscribe. And thank you for patience. That is now. Bye bye. See you again.